In this video, I want to talk about signed binary numbers. So up until this point, all the binary numbers that we saw were unsigned. So they were all positive, 0 or greater than 0. So how can we represent signed binary numbers? So there are two different techniques that I will discuss here. The first technique is called sign magnitude representation, and the second one is the two's complement representation. So let's go over each one of them one by one and see some examples. So for the sign magnitude numbers, the first bit is considered the sign bit, and the n minus 1 remaining bits are the magnitude bits. So let's just take a look at one example. So let's just assume we have an n bit number. So this one is representing the sign, and the rest represents the magnitude. So the sign bit is the most significant bit in the number. As you can see, the most significant bit, if you remember from before, is the leftmost bit in the number. So for positive numbers, the sign bit is going to be 0, but for the negative numbers, the sign bit is going to be 1. So as you can see, this is very similar to the way that we represent signed decimal numbers. So if, for example, I say I have a number 126, if it's positive, we either don't show the sign, or we just show it like this. On the other hand, if I want to have negative 126, I have negative 126. So since we have to put this negative sign to the left of the number in order to signify that this is a negative number, we have a similar thing for the sign magnitude numbers as well. If it is a negative number, we represent it with a 1 in the sign bit, but for positive numbers, we just put 0, similar to when we represent positive numbers, positive decimal numbers, that we usually don't put this positive sign. So let's just take a look at a couple of examples. So let's just say we want to find the representations of positive and negative 6 using a 4-bit sign magnitude representation. So first of all, for value 6, if you remember from before, 6 could be represented as 1, 1, 0. Do you remember that? This one had a weight of 2 to the power 2, this one had a weight of 2 to the power 1, and this one had a weight of 2 to the power 0. So if I write this down, it's going to be 1 multiplied by 2 to the 2 plus 1 multiplied by 2 to the 1 plus 0 multiplied by 2 to the 0. So 4 plus 2 equals 6 in base 10. But you can see that the representation for 6 only requires 3 bits, but we specified here that we want to have 4 bits for the representation, and that extra bit is to show the sign. So since positive 6 is a positive number, and based on this convention, we have to put 0 as the sign bit. So the sign magnitude representation of positive 6 is 0, 1, 1, 0. What about the representation for negative 6? Since for sign magnitude representation, if the number is negative, the sign bit should be 1. So we have 1, 1, 1, 0 as the 4-bit sign magnitude representation of the value negative 6. So one thing that you should consider here, as opposed to what we have learned before. Before we were saying that if we have, let's say, a 4-bit number. So, and this one, let's just say it's unsigned. All of these had some weight associated with them. So this one had a weight of 2 to the 0, this one had a weight of 2 to the 1, this one had a weight of 2 to the 2, and this one had the weight of 2 to the 3, right? But as soon as we say that this is not an unsigned number, but instead it's a signed magnitude number, the weight here would completely change. So for a signed magnitude 4-bit, the weight here is 2 to the 0, the weight here is 2 to the 1, the weight here is 2 to the 2, and finally the weight here is going to be -1. So if the value is positive, then this one is 0. So you multiply 0 by its weight, -1. The result is going to be positive. If the value is negative, the value here is going to be 1. When you multiply it, you get a negative decimal value. So based on this, the range of the values that can be represented using a signed magnitude number is going to be different. The range, if I want to show it mathematically, is between 2 to the negative 2 to the n minus 1 and negative 2 to the n minus 1. So let's just do some testing for some basic numbers. Let's just assume we have a 4-bit signed magnitude number. So what is the highest value that can be represented using 4-bit signed magnitude number? So since we are going for highest value, it should be positive. So that means that the signed bit is going to be 0, and then we have 1, 1, 1 as the highest possible value, which translates to 7. On the other hand, what is the most negative value, or the smallest possible value? It's going to be 1, 1, 1, 1. So this is again the signed bit, right? This is the first one, is the signed bit, which means that this one is representing -7. So now if I replace n with value 4 here, 2 to the 4 minus 1 is going to be 2 to the 3 minus 1, which is going to be 7. And if you do the same thing here, negative 2 to the 4 minus 1 equals negative 2 to the 3 minus 1, which is going to be -7. So that's one difference between the unsigned number and signed magnitude numbers. So now, one important property that signed magnitude numbers or any signed number should satisfy is that whether addition works properly. So for example, for decimal numbers, when you add -7 and +7, so -6 plus 6, the result should be 0, right? So let's just see if this is the case for signed magnitude numbers. So this is the representation for -6, and this one is the representation for +6. So these were 6, I think I said 7. So let's just do the addition and see what is the result. So we have 0 plus 0, the result is 0. 1 plus 1, the result is 0 with 1 carry to the next. 1 plus 1 plus 1 is 1, 1. We put 1 here, we carry 1 to the left. and then we have 1 plus 1 plus 0, which is 0, with a carry to the left, and this one doesn't add with anything, so this is going to be the final result. So since we are working with 4 bits and this 4 bit is fixed, that means that this last bit is overflow, and we will ignore it, right? So let's just ignore this. What is the equivalent value for this number that we got as a result? So first of all, the sign bit is 0, so that means that it's a positive number. Then we have 1 with the associated weight of 2 to the power 2. Then we have 2 zeros, each one of them have a weight of 2 to the 1 and 2 to the 0 respectively. So the result here is positive 4, which is wrong. So we added negative 6 with positive 6, and instead of getting 0 as a result, we got positive 4. So that is one of the problems with sign magnitude numbers, in which addition doesn't work properly. There's another problem with sign magnitude numbers, and that is there are 2 representations for 0. Again, let's just assume this is a 4-bit sign magnitude number. So as I said before, the most significant bit is the sign bit, right? And the rest are the magnitude bits. So the magnitude for these 2 numbers is 0. However, the sign bit for one is 1 and for the other one is 0. So this is basically negative 0 and this one is positive 0. But we don't have such a thing as positive 0 or negative 0. We only have 1 0. So this is the second problem with sign magnitude numbers. So in practice, sign magnitude numbers are not being used, especially for the cases that we require addition or representation, or more specifically one-to-one representation between decimal numbers and binary numbers. So because of these 2 issues, there is a second approach to represent sign numbers, which is called 2's complement numbers. So 2's complement numbers don't have the same problems as sign magnitude numbers, which means that addition works properly for 2's complement numbers, and we have only one single representation for 0. So let's just see how we can calculate 2's complement numbers for sign numbers. So before we do that, let's just see what is the representation for 2's complement numbers. So let me just quickly summarize what we have learned so far. So let's just say we have an n-bit unsigned number. So for n-bit unsigned numbers, starting from the least significant bit, we had 2 to the 0, then we had 2 to the 1, all the way to 2 to the n minus 1. These were the weights associated with each bit of the unsigned number. For the sign magnitude numbers, with the same representation of n bits, what we had was 2 to the 0, 2 to the 1, all the way to 2 to the n minus 2. For the last bit, the weight was negative 1. As you can see, the last bit or the most significant bit in a sign magnitude number has a weight of negative 1, which means that it only represents the sign. It doesn't have any additional magnitude. For the 2's complement numbers, this is a bit different. For the 2's complement number, the last bit not only has the sign information, but also it has a weight as well. So this is 2 to the 0, 2 to the 1, 2 to the 2, all the way to 2 to the n minus 2. And this one, I write it here. It's actually negative 2 to the n minus 1. So basically what happens is that the most significant bit in the 2's complement number not only represent the sign, but also it has a magnitude associated with it too, right? And that is the strength of 2's complement number, and that is why it can avoid some of the problems that sign magnitude numbers had. So here you see the mathematical representation of a 2's complement number. So the most significant bit here, I show it with a n minus 1, so these should be capital N. Has a weight of negative 2 to the power n minus 1. So don't confuse that this is not equal to negative. Let me just erase this. So don't confuse it with this, right? So the negative is the sign of 2 to the n minus 1. You don't take negative 2 to the power n minus 1. So as I was saying, the most significant bit has a weight of negative 2 to the n minus 1, and the rest have weights of 2 to the I. I can change from 0 to n minus 2 as I shown here. So based on this, what is the most positive 4-bit number that we can have? So the most positive 4-bit number that we can have is going to be 0, 1, 1, 1. So as you can see, this is similar to what we had for the sign magnitude number. But what about the most negative 4-bit number that we can have in a 2's complement system? The answer to that is 1, 0, 0, 0. You might ask why? Because unlike sign magnitude number, in which the most significant bit only were representing the sign, for the 2's complement number, not only represent a sign, but also it has a weight associated with it too. And as you can see, the weight is 2 to the n minus 1. So if I convert this into its decimal equivalent, it's going to be 1 multiplied by negative 2 to the 4 minus 1 plus 0 multiplied by 2 to the 2 plus 0 multiplied by 2 to the 1 plus 0 multiplied by 2 to the 0. 2 to the 0. So this is 2 to the 3 with a negative sign. So this is going to be negative 8 plus 0 plus 0 plus 0. And the answer to that is 0. So the most positive 4-bit number in 2's complement system is going to be positive 7. And the most negative 4-bit number is going to be negative 8. So again, I will repeat, in sign magnitude numbers, the most significant bit only represent the sign. But in 2's complement numbers, not only represent the sign, but also it has a weight associated with it too. So based on this, the range of the values that can be represented using an 8-bit 2's complement number is going to be between negative 2 to the n minus 1 and positive 2 to the n minus 1 minus 1. So if you plug 4 as the number here, the range is going to be between negative 8 and positive 7, basically the calculations that we had here. So now you might ask, how can I find the 2's complement of a number? Or in another word, how can I take the 2's complement of a number? This is equivalent to flipping the sign of a number. So if you had, let's say, negative 10 and you want to flip the sign, you basically just change the sign in decimal numbers. Or if you had positive 33, you wanted to flip the sign, you could just do like this, only change the sign. For 2's complement number, the method for doing this involves 2 steps. The first step is that you invert the bits. Basically, any bit in the number that is 0, you invert it to be 1, and any 1, you invert it to be 0, and then you add 1 to the whole number. So let's just go for a very simple example. So let's just assume we have this positive number, 3 in base 10, and we have represented it in 2's complement form, 0, 0, 1, 1. So I can verify that this is positive 3. So the first one has a weight of 0 to the multiplied by 2 to the negative 3 plus 0 multiplied by 2 to the 2 plus 0, 1 multiplied by 2 to the 1 plus 1 multiplied by 2 to the 0. So this is 0, this one is 0, and then we have 2 and 1, which equals 3, right? So now let's just say we want to create negative 3 as a 2's complement number using 4 bits. As I said, we write down the number, we flip all the bits. So basically anywhere we had 1, we put 0, and anywhere we had 0, we put 1. So this is the first step. The second step is to add 1 to this number. So we have 1, 1, 0, 0 plus 1. So 0 plus 1 is 1, there is no carry. Then the next one is going to be 0, and then 1 and 1. So the value for negative 3 in a 4-bit 2's complement number is going to be 1101. And we can easily verify that too. So this one had a weight of negative 2 to the 3 plus the next one had a weight of 2 to the 2. The next bit had a weight of 2 to the 1. And finally the last one had a weight of 2 to the 0. So we have negative 8 plus 4 plus 1, this last one, equals negative 3. Let's just take a look at another example. We want to take the 2's complement of 6, positive 6 basically. So we have 0, 1, 1, 0. The first step was to flip all the bits. So the first bit, the least significant bit, is 0. It will be 1. Then the next one is 1. It will be 0. The next one is 1. It will be 0. And finally the last one is 0, which will be 1. The next step was to add 1 to this number. So we have 1 plus 1. It's going to be 0 with 1 carry to the next bit. Now 1 plus 0 is going to be 1. And then there is no carry for the rest too. So it's going to be 0, 1. So 1, 0, 1, 0 is the 2's complement of negative 6 using 4 bits. And again, I can verify it as well. So this one was 1 multiplied by negative 2 to the 3. So this is for this bit, and then 0 multiplied by 2 to the 2 plus 1 multiplied by 2 to the 1 and plus 0 multiplied by 2 to the 0. So this one is negative 8 plus 0 plus 2 plus 0, which if you add all these up, it's going to be negative 6 in base 10. So just by looking at the 2's complement number, the most significant bit, you can see whether the number is positive or negative, right? So this is common between 2's complement and sign magnitude. But what is different is that in sign magnitude number, the most significant bit only showed the sign without any weight. In 2's complement numbers, the most significant bit not only shows the sign, but also it has a weight associated with it too. So let's just look at another example. What is the decimal value of the 2's complement number 1001? So let's just do it in two ways. The first way is let's just use the associated weights. So we have 1001 in base 2, which is equal to 1 multiplied by negative 2 to the 3 plus 0 multiplied by 2 to the 2 plus 0 multiplied by 2 to the 1 plus 1 multiplied by 2 to the 0. So it's going to be negative 8 plus 0 plus 0 plus 1, which makes the result to be negative 7 in base 10. Another way of doing it is just by looking at this number and looking at the most significant bit. Since we know that it's a 2's complement number and we know that it is 4 bits, and we know that the most significant bit is 1, this is a negative number. So what we can do is that we can find the positive equivalent and then convert that into a decimal number. So 1001, we have to flip the bits, which makes it 0110, and then we add 1, which when we add 1 it's going to be 0111, and you remember it from before that 0111, if you convert it to decimal, is going to be positive 7. So I can do it again here. Negative 2 to the 3 plus 1 multiplied by 2 to the 2 plus 1 multiplied by 2 to the 1 plus 1 multiplied by 2 to the 0, which is going to be 7. So that means that the original number was negative 7. So as you can see, the procedure for finding 2's complement of a binary number does not change. If the original number is positive, when you go through this two-step process, you make it negative. If the original number is negative, when you go through this two-step process, you make it positive, right? Similar to the way that you find the positive or negative value of a decimal number. So basically, if you have, again, you have 45, you want to make it negative, you basically multiply it by negative 1, and that's going to be negative 45. Now if you want to go back to 45, you multiply this negative number by negative 1 again. As you can see, the forward and backward processes are exactly the same. So the same is true for 2's complement numbers. If the input number is positive, when you take the 2's complement, the output is going to be negative. If the input number is negative, when you take the 2's complement, the output number is going to be positive. So now let's see how addition works, because one of the problems with sign magnitude number was that the addition didn't work properly. So let's just see how it works using 2's complement numbers. So this is a 2's complement representation of positive 6, and this one is the 2's complement representation of negative 6. So now we want to add these two together. So we have 0 plus 0, it's going to be 0, no carry to the next bit. We have 1 plus 1, which is going to be 1, 0, 0, we have 1 carry to the next bit. Now we have 1 plus 1 plus 0, which is going to be 1, 0 again, so 0, 1 to the next bit as a carry. And then we have 1 plus 0 plus 1, which is again 1, 0, so 0, 1 carry, and then this thing directly goes down. So since we are working with fixed number of bits, and that is 4, basically this overflow is being ignored. So we ignore the overflow, and what we are left with is 0, 0, 0, 0, which if you calculate its decimal equivalent, it's going to be 0 in decimal numbers. And as you can see, the same procedure that didn't provide correct result in sign magnitude numbers, you can get a correct result using 2's complement numbers. So let's just take a look at another example. So here we want to add negative 2 and positive 3 here. So this is negative 2, this is positive 3, and we expect the result to be 1. So let's just see if the result is correct. So we have 0 plus 1 is 1, no carry. Then we have 1 plus 1 is 1, 0. So we have 0 here, 1 goes to the next bit. 1 plus 1 plus 0 is going to be 1, 0. So we have 0, 1 here. 1 plus 1 plus 0 is going to be 1, 0. So 0 and 1 carry to the next. And then this one comes down directly because there is no other number. And again, since we are working with fixed bits, that means that this overflow is eliminated, and what we left with is 0, 0, 0, 1, which if we convert it is going to be 1 in decimal numbers. So now that we have seen these different representations, so again, let me just summarize it. We saw unsigned numbers, we saw sign magnitude numbers, and we saw 2's complement numbers. Let's say we want to work only with unsigned numbers, right? So in unsigned numbers, 0, 1, 1, 1, 0 is equal to 0, 0, 0, 1, 1, 1, 0. What does it mean? It means that the number of zeros to the left of the number does not change the value of the number, right? So if you calculate these to find the decimal equivalent, you see that these two are exactly the same. For sign magnitude and 2's complement, this is not as straightforward. Why? Because the most significant bit for sign magnitude and 2's complement numbers represented the sign. So how can we increase the width or the size of a number from n to m? Depends on the type of number that you have. So based on that, we can do either sign extension or 0 extension. So this is an example of 0 extension. Why? Because we added how many number of zeros that we wanted to the left of the image, right? The left of the number. So let's just go into more detail. So for the sign extension, the sign bit will be copied to the most significant bits. So let's just say we have this number 100111, and we know that it is a signed number, right? So in this case, let's just say we want to extend this number from 6 bits to 8 bits. So this is 6 bits. We want to extend it to 8 bits. So in this case, we copy the sign bits to the left. So we have 1 1 and then 1 0 0 1 1 1. So this is exactly similar as the input number. However, these ones are basically copies of the sign bit that we had. So if we do this, the number value stays the same, and you can verify it using 2's complement numbers. So let's just take a look at some examples. We have here, we want to have a 4-bit representation of 3. So for the value 3, since it's positive and it is shown using 3 bits, 0 1 1. If you want to extend it using sign extension, the sign bit is this bit, right? So since you want to make it 4 bits, you basically copy this into the 4th place. It was the same if you want to make it 8-bit too. So an 8-bit representation, it was 0 0 0 0 0 0 1 1, as you can see here. What about if we have a negative number? So for negative number, the same thing happens. So first of all, we want to show a -5 using binary numbers. So we at least require 4 bits to do the representation. For +5, we could show it using only 3 bits, right? Because positive numbers, using 3 bits, we can represent values between 0 and 7, right? But for negative numbers, to show values between -8 and +7, for example, using 2's complement numbers, we required 4 bits, right? So since -5 is already represented by 4 bits, you don't have to do anything, right? But if you wanted to, let's say, represent it using 8 bits, right? If you want to represent it 8 bits, that basically means that this is the sign bit. You extend it, you repeat this bit how many number of times that you want. So this is an 8-bit representation of -5 by sign extension. As I said, using sign extension, it preserves the value of the number. However, for 0 extension, what we do is basically copy zeros to the most significant bits. And for negative values, the value of the binary number would change. So let's just take a look at some examples here. Again, we start with an example of a positive number. So we have +3, and we want to 0 extend it to make it 4 bits. So this is +3. Sorry, this is +3 itself. +3 only requires 2 bits to be represented. So since you want to 0 extend it, to make it 4 bit, you add 2 zeros to its left. What about if you want to make it 8 bits? The same applies. You copy 6 zeros to its left, because the original number only required 2 bits to be represented. But what about -5? Again, -5, no matter if it's being represented as a sign magnitude number or a 2's complement number, it requires 4 bits, right? So for 4-bit value, you don't have to basically do anything. But if you want to make it 8 bits, then using 0 extension, you add zeros to the left of the number. But one thing that you notice here is that in its original representation, the most significant bit that was also representing the sign was 1. That meant that the number is negative. But in its extended 0 extended version, the most significant bit is now 0. So that means that the value changed from a negative number into a positive number, right? So this is something that you need to consider. If you are working only with unsigned numbers, 0 extension is fine, right? Because 0 extension is exactly the same as sign extension. Because for positive numbers, the sign bit is 0, right? But for negative numbers, if you use 0 extension, you're practically changing the value of the number. So for negative numbers, 0 extension produces wrong result. So you instead have to use sign extension. So even though, as you can see, sign extension is more robust and more accurate, it's not necessarily the best for all applications, right? Because if you know you always work, for example, with unsigned numbers, I think 0 extension implementation is much simpler than sign extension, right? So based on all the things that I have discussed, let's just summarize the range of the values that we can have for unsigned, sign magnitude, and 2's complement number again. So if we have n bits to represent a number, if the number is an unsigned number, you can show values between 0 and 2 to the n minus 1 in the number. So for example, if n is equal 4, this translates to values between 0 and 15. So that's exactly what you see here in the following example. Using 4 bits, you can show values between 0, 0, 0, 0 and 1, 1, 1, 1. Basically between 0 and 15 using an unsigned binary number representation. However, if you are using a sign magnitude representation, in that case, you can only show values in the range between -7 and +7. So this is the same representation but more visually. So as I said before, you have 2 representations for 0. So 0, 0, 0, 0, which is representing +0, and 1, 0, 0, 0, which is representing -0. So as I discussed before, this is basically meaningless because we don't have positive or negative zeros. We only have 1 0. As for the most positive value of using sign magnitude representation, we can have 0, 1, 1, 1. And as for the negative, most negative value representation, we can have 1, 1, 1, 1. In 2's complement number, the range is a bit different. You can represent values between -8 and +7. And this is a visual representation of 2's complement numbers using 4-bit representation. So we have 1 here, we have 0 here, we have 1 here, we have 2, 3, 4, 5, 6, 7. As for the negative values, if you look closely, they seem to be rotated. And the reason for that is the weight associated with the the most significant bit was negative 2 to the n minus 1, or for 4 bits it was negative 8, right? So this is something that you have to consider, that the order is different between positive and negative numbers, right? So if you look here for the unsigned number, you have 0, 0, 0, 0, 0, 0, 0, 1. You go one by one, and basically between each one of these and the next one, one value has changed, right? But but here, when you go from 0 to the right, you are basically adding one value. When you go from 0 to the left, you are subtracting one value. So that is a bit different than unsigned numbers. So in this video, we went over signed binary numbers. We introduced two different systems for representing signed binary numbers. We saw signed magnitude numbers, 2's complement numbers, how we can calculate them, how we can convert from one another. Then we saw how we can extend the sign of a number, which we said it is especially useful for negative numbers. And also we saw how we can zero extend a number, that we said it's most useful for unsigned numbers. And finally we compared the different number systems